All right, so we're going to continue our discussion now in this video with some curve sketching. I've got another example up on the board, so we'll just run through that six-step process that I outlined a while back. So the first step is always the domain. And in this particular function, nothing to worry about again. We've got a cube root here, we've got a cube root here, so no issues. Domain would be negative infinity to positive infinity. The second step would be the end behavior then. We don't have any asymptotes, so our end behavior discussion would be the limit as x goes to positive infinity and the limit as x goes to negative infinity. All right, so remember, there are dominant parts to this, and you can more or less get a basic idea by looking at this as a product. If I take a big positive number and I plug it in here, that's going to give me a positive quantity. If I take a big positive number and plug it in here, it's going to give me a positive quantity as well, right? A positive square, a cube root, and a positive cube root. So this guy would need to be positive infinity. Now, when I take a negative number and I plug it in here, this would be negative, right? The cube root of a negative is negative. Here, though, this being squared would always be positive. So I would have a negative times a positive, which is negative, which means that I have to be at negative infinity, okay? So now that's going to give my graph a starting value here. Let me change the way I wrote that. A starting value here where it might look like this, and an ending value here where it might look like this, right? As x goes to positive infinity, we want to go to positive infinity. If we go to negative infinity, we want to end at negative infinity. The rest of the problem is going to be us figuring out what happens in between. Okay, so those are the limits, the end behavior that I'll be looking for. Now we're ready to move on to step 3, which is the first derivative test. And the simplified first derivative of this is 2 minus x over x to the 2/3, 6 minus x to the 1/3. Okay? And so I would set this equal to 0 to solve it. And you could see very quickly our critical value of x equals 2 is going to be a big part of this, right? If I multiply that denominator into that, I can solve this for 2 and I get a critical value. But there's also more. Remember, the domain was everything, but if I look carefully down here, I can't have a 0 and I can't have a 6 in my denominator. So we have two non-differentiable points. We have x equals 0, we have x equals 6. Both of those are non-differentiable points that need to be included in our critical value list and need to be put on our number line. All right, because again, they could be maxes and mins. That's what we're looking for in that first derivative test. So I'll take that first derivative number line here, and I'm going to put my 0, 2, and 6 on. I'm going to search a -1, a 1, a 3, and a 7. Pick whatever numbers you want as long as they're in the interval. And I'm taking these red numbers back into this guy. And again, don't overwork yourself here. All you care about are pluses and minuses. So, for example, if I take this 1, let's just keep it easy. If I take this 1 right here and I plug it in right there, that's going to give me a positive value. If I put a 1 here, it's going to be positive. If I put a 1 here, it's going to be positive. With all of those being positive, that tells me that I'm going to have a positive right there. I don't care what number it is, I just care positive or negative. And you could do the same for all of those red numbers. Just mark the pluses and minuses and look what the relationship's going to be with division and multiplication. When you do this, we end up with a plus there, a minus, and then a plus. Okay? So we would be increasing from negative infinity to 2, as well as 6 to positive infinity. Now, some people might be wondering, well, why didn't you skip over 0? Well, remember, 0 is a point on the graph, okay? When you see the graph, it's going to be a little easier to understand why I didn't break it at 0, why I just continued it across. So don't sweat it right now. Once you see the graph and see how this is going to play out, you'll be able to better understand. And if you did split it apart, once you see the graph and you want to circle back, you can certainly do that as well, okay? So there's our increasing. Our decreasing now would be 2 to 6, and we would have a relative max it looks like at 2 f of 2 and a relative min at 6 f of 6. So there's your first derivative test. And again, if the interval is throwing you off a little bit on that 0, don't sweat it just yet. We can adjust later if we need to, or you can do it however you need to. So there's your first derivative test. So now we'll move on to step 4, which is the second derivative test. The second derivative simplified would be this thing here. So, that's right, x to the 5/3, and then we've got 6 minus x to the 4/3. All right, so I would take this now, I'd set it equal to 0, and from that second derivative, I don't get any new critical values, but we still have to carry down the x equals 0 and x equals 6. Those are still non-differentiable points, and we have to use them in our critical value list for our second derivative. If you go back to that page 110, I pointed out before, those non-differentiable points can be maxes and mins, but if you look back, you can also see they may or may not be inflection points. And so we have to take into consideration this idea of concavity and the non-differentiable points. Okay, so f double prime's number line looks like this, where I'm going to test 0 and 6, or at 0 and 6, and then I'll test actual numbers of -1, 1, and 7. Again, pick whatever you want to pick. Taking these red numbers, going back into here, all I care about are the signs. You know the numerator is always negative. Figure out what these are, pluses or minuses, and then from there put it all together. And we would get a plus, a minus, and a minus for that. So this tells us we are concave up from -infinity to 0, and concave down from 0 to 6, union 6 to positive infinity. And again, I expect questions on why I split that one apart and I didn't split the first derivative one apart at 0. I get all that. Trust me, when you see the graph, you'll see it. And if you made the mistake of splitting it up or not splitting it up, once you see the graph, you can come back, obviously, and adjust how you put this together. Okay, so again, don't sweat it if your intervals are a little bit off going into the graph. Once you get the graph put together, it will all make sense. Okay? Step 5. Step 5 would be the intercepts. So the intercepts for this particular one happen to be 0, 0, as well as 0, 6. So remember to write those as points. Okay, so now let's go ahead and put this graph together. So if I put my x-axis and my y-axis on there, once again, I'm focusing primarily on this guy here, this information here, and right here. This is the stuff that I always start with to get a general picture up there. From there, I can make adjustments as needed. Okay, now another big part of this is continuing to understand that these guys right here, these are non-differentiable points. So expect strange things to happen, right? Expect the non-traditional things to happen. So it looks to me that I would start down here. I would be increasing. I have to go through 0. That's one of my intercepts. I continue to increase to 2. Then from there, I decrease to 6. And then from there, I go back to increasing. Okay? So if this is, let's see, my 6, and if I continue to increase through 0, but 0 is a non-differentiable point, that's actually going to be where I have this vertical tangent line, right? So I'd come through like this, and then my slope would, for the instant, become vertical. And then I would continue to come up like this. And then from there, I would come down to my next non-differentiable point and bounce back up. All right, so let me sketch this in. So I come up through it like this. At the instant I'm at 0, I'm vertical. Then I would come back down and I would go back out. So that point is there, that point is there, and we've got this guy here. Now, let's not only make sure this fits the things that I've discussed, but let's go back through and make sure it fits the concavity as well. So the domain is good, limits are good, increasing up until 2, so it looks like we're at about 2 right here, and there's my maximum value. Then I decrease to 6, there's my other minimum value there, and then it continues to increase. I've got my intercepts marked, and then let's look at the concavity. I would be considered concave up from negative infinity to 0, so that would be our concave up. Then I'm concave down 0 to 6, and then still concave down 6 to infinity. So had this guy been concave up, then it would have come down like this and came around more as a corner, where now what we're dealing with is more of a cusp. So this is an interesting graph in that it's got two non-differentiable points, two very, very different ways of graphing around those non-differentiable points. We've got our vertical tangent here, we've got our cusp right here, and then overall the process has put this together as it should.